Hello everyone, Dr. J here again with another chemistry video, so let's get right into it. Chemical kinetics is the study of the rate at which reactants and products change during a chemical reaction. Reactions can occur over a large range of timescales, such as combustion, which occurs in fractions of a second, or the conversion of diamond to graphite, which occurs over centuries. In this video, you will be introduced to reaction rates, how they can be measured, and how and why both concentration and temperature affect reaction rates. The rate of a reaction depends on how frequently the reactants collide with one another to make products. This depends on the physical states, the concentrations, and the temperature of the reactants. It also depends on whether or not the reaction is catalyzed, which we will cover later in class. More collisions per unit time result in a faster reaction rate. Now, reaction rates can be measured in several different ways. For example, we can measure a change in color, a change in temperature, a change in the mass of a precipitate, or a change in pressure. All of these are ways of measuring changes in the concentrations of the components of the reaction. Measuring these properties of a reaction over a specific period of time allows us to determine a reaction rate for a specific reaction. As an example, let's use a simple reaction where 1 mole of N2O2 produces 2 moles of nitric oxide. To determine the rate, we can either monitor the rate of disappearance of N2O2, that is the decrease in the concentration of N2O2 over a specific time interval, or we can measure the rate of appearance of nitric oxide, that is the increase in concentration of nitric oxide over a specific time interval. The negative sign in front of the expression for reactants ensures that the calculated rate will always be positive when using the reactants to measure the rate. Also notice that while only 1 mole of N2O2 is consumed, 2 moles of nitric oxide are produced. This must be taken into account in the rate expression, and we do this by placing a fractional coefficient for nitric oxide in front of its rate expression. This fraction is simply the inverse of the stoichiometric coefficient found in the balanced chemical reaction. If we were to represent the change in concentration versus time graphically, it would look like this, where the concentration of reactants is decreasing and the concentration of products is increasing. From the equation, you can see that the rate is simply a change in concentration over time, and that can also be represented on the graph, since the axes are also concentration and time. If we take any 2 points on the blue or red curve, the slope between these 2 points, the rise over the run, is the rate, the units of which are also concentration over time. While this gives an average rate over a specific period of time, you can probably see that it is not a very good representation of the reaction rate at the beginning or end of the time interval, where the slopes in those areas are different than that of the average rate. So instead, we can measure the instantaneous rate of the reaction by simply determining the slope of the tangent line at a particular time on the graph. This concept will become more important a bit later on in the video. Now let's take a closer look at the concentration versus time graph. Notice that it is not linear. The reactants undergo an exponential decay, whereas the products undergo logarithmic growth. So the measured rate of the reaction, whether measured as an average or instantaneous rate, is not the same at any 2 points on the graph. This should make it clear that the rate changes as concentrations of reactants change. For example, as the concentration of reactants decreases, the slope of the tangent line also decreases, which means that the rate of the reaction decreases. This also suggests that a reaction with a higher starting concentration of reactants would have a faster reaction rate than the same reaction that had a lower initial concentration of reactants. So concentration has an effect on the reaction rate, but why? To help explain that, I'm going to skip ahead slightly in your textbook and cover a bit of basic collision theory. Let's start with a reaction between ozone and nitric oxide. For a reaction to occur, the reactants must first collide with each other. But it's not quite that simple. They must collide in the right orientation and with sufficient energy to form products. This is called an effective collision. Reactants that do not undergo an effective collision will not form products. So though there may be plenty of collisions within a reaction mixture, not every collision results in the conversion of reactants to products. To increase the rate of a reaction, the number of effective collisions must be increased. One way to do this is to increase the concentrations of the reactants. At low reactant concentrations, the frequency of any collision, let alone an effective collision, is low, so the rate of the reaction will also be low. At high reactant concentrations, more reactant molecules are present, so the frequency of collisions, and therefore effective collisions, will increase, increasing the rate of the reaction. Returning to the concentration versus time graph, as the reactants are used up over time, the concentration decreases, resulting in fewer effective collisions and a slower reaction rate. This is seen either as a decrease in the rate of disappearance of reactants or as a decrease in the rate of appearance of products. Since the rate changes over time, it is common to report the initial reaction rate or the rate of the reaction at time 0, rather than arbitrarily choosing any other time during the reaction. This is determined from the slope of the tangent line at time equals 0. We choose this particular point because at the start of a reaction, there are essentially no products formed. This is important since, as we will see in the next chapter, reactions can also go in reverse, and the rate of the reverse reaction would have to be taken into account when determining the rate of the forward reaction if a time other than t equals 0 is chosen. There is one more thing I want to quickly touch on, and that is how temperature affects the rate of a reaction. This is discussed a bit later in your textbook, but it fits in with what I've been talking about so far with collision theory. So we now know that reactants need some minimum amount of energy to undergo an effective collision, and that energy is going to be in the form of kinetic energy. I'll represent this threshold as a line on the graph. The area under this curved line represents the proportion of molecules that have a specific amount of kinetic energy at a given temperature. I'll call this the low temperature situation. Even at low temperatures, there are still some molecules that have a sufficient amount of kinetic energy to undergo an effective collision, and this is represented by the area under the curve. Now, if we increase the temperature, what happens is that the average kinetic energy of the molecules increases, which results in a greater number of molecules with sufficient kinetic energy to undergo an effective collision. This results in an increase in the reaction rate. A general rule of thumb is that increasing the temperature by 10 degrees Celsius doubles the reaction rate. Okay, so before I summarize, here are a couple of things to think about. We talked about how things like temperature and concentration affect the reaction rate, but so does the physical state of the reactants. So question 1 is, how does the physical state of the reactants affect the rate of a reaction? Question 2, what exactly is happening when an effective collision occurs? Think about chemical bonds for this one. And question 3, how can initial rates be determined if we can't take a measurement at time 0? In summary, a reaction rate is determined by measuring a change in concentration over time. This can be done by measuring the rate of disappearance of reactants or the rate of appearance of products. Reaction rates are concentration dependent, so as the reactants are used up over the course of a reaction, the reaction rate decreases, since there are fewer reactants remaining, leading to fewer effective collisions. This would also mean that starting a reaction with lower concentrations of reactants would result in a reaction rate that proceeds more slowly than one that started with a higher reactant concentration. Another factor that affects the reaction rates is temperature, and higher temperatures generally result in faster reaction rates. In class, we will practice writing the rate equations for reactions and go over some specific examples of how to determine reaction rates with actual experimental data. In the next couple of classes, we will revisit temperature and learn about a couple of other factors that affect the rate of a reaction. I'm Dr. J. Thanks for watching.